So there's one more topic that has to do with NMR, which is actually gets a little bit complicated. However, it's also very powerful and very useful. So it's a really good thing to to learn and to try to focus on. So look at the spectrum that's on this page. Um, it's got these sort of split peaks. There's more than two peaks, even though we only see two different kinds of hydrogen. So three over here and then one over here. So we would expect two peaks. And it looks like we have more than that. But it turns out that really these are the two peaks right here. So it turns out that there's one peak at 2.06 and there's one peak at 5.89. And notice that they give you the integration for the whole group. And if you do some of the math, you can find out that the peak at 2.06 is about 3 times as large as the peak at 5.89. So that's a 1 to 3 ratio. So the 1 to 3. So that makes sense. And so it turns out that the peaks, they've got them colored. So it turns out that the 3 red ones are represented by this peak over here, and the 1 yellow one is represented by this peak over here. So what is all this little bitty parts to the peak? Well, that's called spin-spin splitting. And it is, like I said, an extra complication, but it can also be a powerful tool. And so it turns out that what happens is this one little carbon over here splits these 3 into a peak of 2. And these 3 over here split the yellow one into a peak of 4. So let's talk a little bit more about that. So spin-spin splitting is caused by the interaction, or sometimes it's also called coupling, of spins of nuclei that are they're on carbons one away from each other. And so if you go back and look at some of the previous examples that we've talked about in the previous slideshows, the hydrogens were never right next to each other, so we hadn't had to deal with spin splitting yet. But once you have hydrogens that are on neighboring carbons, they kind of interact with each other. So the tiny magnet of one of the hydrogens will affect the hydrogens on the carbon next over to where it is. And the way that it splits is called the N+1 rule. So what that is that each proton senses how many equivalent protons are on the neighboring carbon, and then its peak is split into N+1. So if you if we look at the previous example, this is kind of how it worked. There you can see that there's 3 over here that we're calling HA. So they're all equivalent to each other. And then here's a different one. HB is different from HA. So notice that HB is influenced by these 3 over here, these 3 HAs. And so the peak that represents HB will be split into N+1, which in this case is 3 + 1 or 4 peaks, right? So there's only one hydrogen, so it will have an integration of 1 because there's only 1 represented by that peak. However, it'll be split into a quartet because of the 3 neighbors. And so if you go back 2 slides, the fact that that 1 was split like this, that makes it a quartet. It's split into 4, even though it's 1 peak and it's equivalent to 1 hydrogen, it's split into 4 little peaks. Going over here, these three, they're equivalent to each other. They're all influenced by the one over here. So notice they're neighboring carbons. So it doesn't happen unless the hydrogens are on neighboring carbons. In this case, there's going to be a peak that has an integration of 3 because of the 3 hydrogens. And it's going to be split into n plus 1. In this case, n is just 1. Is going to be split into 2. So that's where we saw on the slide 2 away, we saw we call it a doublet. So it's into a doublet. So it has an integration of 3 because there's 3 hydrogens. So it's equivalent to the area under the curve is equal to 3, but it's split into 2. And so that means that, so if you see the peak that's split into 2, that means there's on the neighboring carbon, there's 1 hydrogen. If you see something split into 4, that means on the neighboring carbon, there's 3 hydrogens. So you subtract 1 and you know how many are on the neighboring carbon. So make sure that you keep it straight. The integration is equal to the number of hydrogens being represented, but how many it splits into depends on the neighboring hydrogen. So I think we'll look at a few other examples. All right, so here's another example. We see that we have 3 different three different hydrogens, and they've labeled them A, B, and C. Now notice that B over here does not have any neighboring carbons. So we expect this to be a singlet, like we've seen all along. So it's not split by anything. And there's 3 hydrogen there, so it would have an integration of 3. Now here we have 2 and 3, and they're on neighboring carbons, right? So this one we would expect to have an integration of 2 because there's two hydrogen, but it's going to be split into n plus 1 or 4. So it's going to be split into a quartet. This one, hydrogen A, is going to have an integration of 3, but it's only going to be split into 3 because it's only got 2 neighbors, so it's going to split into 3. So let's look down here at so you can see here B is a singlet. It's just 1 peak. It's not split at all. A, we said should have an integration of 3, but it should be split into 3 because of its neighbor. So it is, that's a triplet. And then hydrogen C should be an integration of 2, but be split into a quartet. So it can, you might want to pause and take a look and think about this. They're not really giving us the integration. They're not telling us, but there's two carbons here. So if we were able to get the integration, or you might see the numbers 3 here and 3 here. So these 2 have equivalent area under the curve, even though it's split into 3. This one has 2, so it's 2/3 of these. And just to remind you, as far as where they're located along here, notice that this is the farthest away, so we expect it to be the closest to the TMS tetramethylsilane peak. So it's down here around 1. The hydrogen C, the 2 hydrogens that are here, are next to the oxygen, and so they're going to be more de-shielded. So they're further. They're down. They're down here. They're down here at around 4. And then these hydrogen are on a carbon that's attached to a C double bond O. So it is de-shielding, but not quite as much. And so that peak is here around 2. Now you might not have, remembered. We can look these up. And again, there's forms that I'll be giving you in lab or that are on Canvas that how would you know, is this one more de-shielding or is this one? And we talked about it, and the O, since the carbon is directly attached to the O, it is going to be further left. But then you can also start looking at the splitting, and we know that this has to be hydrogen C because it's split into 4, and we know this has to be hydrogen A because it's split into 3. And so it adds, again, some complexity to it, but in a way you can start to see which carbons are or which hydrogens are on carbons that are next to each other. So here's another example, and let's look at it. So we've got 2, and you may not have noticed it at first, but notice that these 2 are identical to each other because of symmetry. So there's 4 hydrogen B's, and there's 2 hydrogen A. And we can see that hydrogen B's are attached to the chlorine, so they should be much further to the left, being more de-shielded. So that's over here. And then we have these should be further to the right. Now, let's see about splitting. So hydrogens A, there's 2 of them, so they have an integration of 2, meaning the area under the curve will be equivalent to 2 hydrogen. But they're split by 4. There's 4 of them there. So n plus 1 will equal 4 plus 1 or 5. So we expect this to be into a pentet, or a 5 peak. So here we see it 1, 2, 3, 4, 5. Hydrogen B, there's 4 of them, so the integration should equal 4, meaning the area under the curve should be equivalent to twice as many as peak A. And we'll look at that in a second, but there's 4 of them, but they're only split, they're neighbors, there's only 2 neighbors, so they should be in a 2 plus 1, or they should have an integral of 3. So that's why this is a triplet and this is a quintet. They did give us some integration values here, and you can see that hydrogen B is twice as much as hydrogen A. So indeed, this is equivalent to 4 hydrogens, and this is equivalent to 2 hydrogens. But the splitting is what's interesting. So we consider that 1 peak, and usually, if you want to know what is the location of the peak, generally you find the middle. So if it's an odd number, just take the center peak and read it off there. So that's where they got 3.75. This one's odd. That one's about 2.2. If it's an even number, then go halfway between the 2 middle ones and read it off. All right, here's one more example. So this hydrogen over here is not split by anybody, so it should be a singlet because it's way over here. And we know that when the hydrogen's directly attached to a carbonyl group, it should be way far here. So that's this carbon right here. And it's purple. You can see that they've got the same colors that they've labeled them. So this kind of fuchsia purple at 8 is this hydrogen here. Now here we have hydrogens on neighboring carbons, and I hope that you can see that all the purple ones are identical because of the symmetry. And so there's 6 purple ones, and there's 1 orange one. So our orange one will be split by 6, so that's 6 plus 1. So that should give us 7. Well, now here, if you look at that, it's sort of hard to tell that that's 7, but what they've done is they've magnified it. So you can see that, in fact, it is 1, 2, 3, 4, 5, 6, 7. Sometimes some of the little ones on the end get missing. And so sometimes they try to magnify it for you so that you can see, or, if it doesn't work out exactly, you can assume, well, they're tiny little ones that we can't really see. But so that's what would you call that? A heptuplet, a 7. And then these 6 are only split by 1, so that's why we see the doublet. 1 plus 1 is 2. So this purple peak has an integration of 6, meaning there's 6 hydrogen, but it's split into a doublet. This orange one has an integration of 1, but it's split into 7 because of its 6 neighbors. This one's not split into any because it's all by itself. And then if you look at the integration that they've given you here, if you divide by the smallest one, 12.9 divided by 12.9 would be 1. So there's one hydrogen. 13.3 divided by 12.9 is pretty much close to 1. So again, there's one hydrogen here. And then 77.5 divided by 12.9 will give you 6. So we see the integration. And we know that these are the two that are connected next to each other because of the splitting. Okay, so the spin splitting comes about because of the hydrogen on the neighbor. Right, so, oops, sorry. So if this is the carbon in question, carbon A, the hydrogen on carbon A, it can sense the spin direction of the hydrogen on carbon B. And so that one can either be with the applied field or against the applied field. And so here's what happens. If the green represents the normal required resonance, which would be the actual peak, the number where it would lie on the x-axis. And let's say that HB is aligned with the field, the magnetic field. What happens is that the effective field is slightly weaker, so the amount of frequency required is a little bit less. And so what's happening is the HB is actually de-shielding, and that shifts slightly to the left. So by this pink amount, it's slightly to the left. If the HB is spinning against the magnetic field, then the net required from the spectrometer is more by the same pink amount, but this time it's more. And so that's a little bit more shielding, and it shifts to the right. And so, and then the fact that on neighboring hydrogens, half of them will be with the field and half will be against, and so that's why half of them will shift right and half of them will shift left. So where this point would be where it would normally be if it didn't have any neighbors, now it's split into two. So again, we count the center as sort of the location, but we see a doublet. So this pretty much says what I just said. So again, if the neighboring hydrogen has an alpha spin, meaning with the field, the spin to require resonance to flip will be less than normal. So that means it's de-shielded and it shifts to the left. If HB has the beta spin, which is against the magnetic field, the required field will have to be overcome to the opposite. And so that's shielding. So the hydrogen is shielding the hydrogen A, and so the spin will shift to the right. And since there's many molecules, about half will have the HB and half will have the positive spin and half will have the negative spin, and so that's why it's split into two, one to the left and one to the right. And like I said, we still read the delta, the value, as the center point. So what if there's, okay, so I'll show you that in a second. So the peak at HB has exact reciprocity. So it means that the distance between them is going to be the same for A and B. So we call that the coupling constant J. So if you look back at some of the previous examples, the distance between the peaks will be the same if those two hydrogens are connected to each other. So this J is called the coupling constant. That's not something we'll use too much in this class. Maybe if you go on and do more with NMR. All right, so how do we explain multiple peaks? So here's what's happening. So what if hydrogen is split by two protons, two neighbors? So what do we have? Either both neighbors can be with the field, and so it decreases the frequency by two little pink arrows, so quite a bit. So it shifts to the left. And or if both of the neighbors are against the field, then you have to overcome both of them, and so this will shift to the right. But notice that if we have two neighbors, the probability of having one with and one against, so there's four possibilities, both with the field, both against the field, or one with and one against. And there's two possibilities here because of the one with, one against, or one against, one with. And so there's two possibilities. So that gives us three. So we have two that stay on the normal place where the black is the same as the green. They don't move. We have one that'll shift to the right and one that'll shift to the left. So that's where we get the triplet. So here you can see. So if two of them will not affect the location because there's one with, one against, one against, one with, or if they're both against, it'll shift to the right, or if they're both with, it'll shift to the left. So that's why we get a triplet. And again, we read the peak, the middle peak, and also you notice that the middle peak is twice as high because there's two chances. And so if there's three neighbors, the pattern gets even more complicated. You could have all three with, all three against. You could have two with and one against, and there's three possibilities of that. Two against, one with, and again, there's three possibilities of that. So you end up with a quartet, and you can see that it's a 1 to 3 to 3 to 1. Again, the original peak would have been here, so you're going to read that on the delta scale. And of course, it just you can build all of these to get the 5, 6, 7, etc. All right, so we saw this one already, but I just want to point it out because it's a very useful pattern to recognize is when you have an ethyl group. So an ethyl group is always a 3 split by 2, 2 split by 3. So the 2 hydrogen will be split into a quartet, which you see here, 1, 2, 3, 4. And notice it's not perfect, but we're not, these are instruments that are due to error. There's some error involved. So, but that pretty much looks like a quartet to me. And then the 3 will be split by 2. So that will give us a triplet. So that's that right there. And then the H on the O will be as a singlet. Even though they're on neighboring carbons, the O's are never, H's on O's aren't split by anything. So we just see a singlet. But notice here a couple of other things too. So the peak that is due to these 2 hydrogen should be further deshielded because of the O. And so this peak is the quartet because it's got a integration of 2 because there's 2 hydrogen, but it's split into a quartet. And because it's closer to the O, it's further to the left, it's further up downfield because it's deshielded. And then this one should be further to the right. And what it's really hard to tell, but the distance between peaks is the same as the distance between peaks because these are the 2. So if you had a really complex molecule and there was some other splitting, you could tell which were the peaks that went together because the distance between peaks should be the same if they're neighbors. That's what that J coupling constant is. Here's another example. Here we have 3 hydrogen, and notice it has no neighbors. So this should be an integration of 3, and it should have no splitting, so a singlet. And here we have some splitting, so these are a neighbor. So we should have 1 split by 3, so it should have a integration of 1, but it should be split into a quartet. This one is 3 split by 1, so it should have an integration of 3, and it should be split into a doublet. So let's look at the arrow. So this one here, this is our doublet. And here's the hydrogen attached to the chlorine, so that's why it's so far down toward the left. It's also attached to this carbonyl, so it's the most deshielded. So that's that one. And notice that it is split into a quartet. And then this one is the singlet, and here's the peak. Now it's a little bit deceiving. You know, we have this has an integration of 3, and this has an integration of 3, and this has an integration of 1. So these are equivalent in terms of area under the curve, but because there's 2 peaks, you have to add them together. So it's not always, you can't always tell by looking at how tall the peak is, how, you know, the relative amounts. And you would probably be either given the integration down here below so you could figure out these ratios, or more likely you probably see the numbers written there, 3, 3, 1, so that you know the ratios. So anyway, that's the splitting. And again, it's hard to see, but the coupling, the distance between those two and these two here will be the same. So the same distance. Sometimes you get some really complex splitting, and this class is not, we're not, you know, sometimes if you get complex splitting, you just say, okay, that's complex splitting. You can't tell if it's a triplet or a quartet, but it makes sense that it's complex. And so it's not always going to be something that you have to identify perfectly. And again, this one's not perfect either, because that's what a real spectra looks like, although it can't always be perfect. But if you look at this, look, you know, we have these two are split by 2. So we expect that to be a triplet, and it is. And it is the furthest to the left because it is the closest to the withdrawing groups over here. So that makes sense. So this is a triplet, and it has an integration of 2, and it's split into 3. This one over here has 3, and it also has 2 neighbors, so it's split into a triplet as well. So that's the triplet. I know it looks kind of funny here, but that's a triplet. There's 3 different peaks. And so this has an integration of 3. You can see it's a little bit bigger, but it's also a triplet because both of these have 2 neighbors. Now this one, in a way, you might say, well, it's got 3 plus 2, it's got 5 neighbors, so it should be a sextuplet. It should have 6. But the problem is, because there's different coupling here, because the green ones are not equivalent to the red ones, it's not going to split it really perfectly. So you could say 1, 2, 3, 4, maybe there's 6, but it's hard to tell. But anyway, it is complex, and that makes sense because you've got these 2 split by these 5. And because, so it's sort of like they're being split by these 2 and split by these 3, and so you can't really recognize any pattern, but it would have a integration of 2 because there's 2 hydrogen in that peak, 3, 2, and 2. And so I don't think it's wrong, especially at this level, to say, well, there's complex splitting. I can't identify if it's a septuplet or a hexuplet or 5, 6. I can't tell. I'll just call it complex, and that's okay. So how do you know if when will there be splitting? Well, if we have chemical equivalent protons, they won't split each other. And so, you know, if they're on the same carbon, we've kind of already identified how you know how many peaks there's going to be. Well, it's sort of similar. So if you've got all the same hydrogen on the same carbon, they're all the same, they're equivalent, so they're not going to split each other. We're just going to get a single peak here with these 3 hydrogen. And then also, you know, if you've got a symmetrical molecule, these 4 hydrogen are equivalent. And so again, they're not going to split each other because they are totally equivalent and they're feeling each other the same way. So that's one general rule, if they're on the same carbon or if they're equivalent within the same molecule. And then again, just some reminders, the signal of a proton that has n equivalent neighbors will split into n plus 1 peaks. And it's got a coupling constant J. The J's will be the same between the 2 groups that are coupled together. So if 2 groups are coupled together, they have the same J coupling constant. If protons are further than 2 away, they will not split each other. So if you look back at that last example, the middle two are the only ones that split their neighbors because you have to be right next to each other. And hydrogens on oxygen, so OH protons do not split the signal, even if they are adjacent, because the oxygen just gets in the way. All right, so we'll be doing a little bit more with splitting in the lab, and practicing with that a little bit more and on your homework. So the last topic that I wanted to cover was NMR, so dealing with carbons rather than hydrogen, and that can be very useful. We won't be doing nearly as much of it in this class, but you should be at least a little bit familiar with it. The problem with NMR is that only about 1% of all carbon is carbon-13, and so it can only detect, remember, it can only detect odd masses, and so it can't detect any of carbon-12, and since only 1% of carbon is carbon-13, the peaks tend to be really small, and so sometimes the peaks blend into the background. So if you've got some background like this, and you know, is this a peak right here? Let's change the color. Is this a peak right here, or is it just part of the noise? And it'd be really hard to see them because they're such small peaks. So what happens is we use this technique called Fourier transform. There's Fourier transform NMR. There's also, you can also do Fourier transform IR, which is basically the Fourier transform is what's described down here. And the technique uses signal averaging. And so if you have what you do is do hundreds of scans over a short amount of time. And so what happens is the background noise cancels itself out. So like, you know, if the background is kind of doing like this one time, but then kind of upside down the next time, what happens is if you average them all together, they'll sort of smooth out over time because the ups and downs will cancel each other out because it's just random noise. So they average each other out. So if you do a bunch of scans like that, then this one with the Fourier transform might look more like that. And then you see, oh yeah, that did not average out. So that really must be a peak. So that's just a technique that's used. It's not a real important thing to remember. I mean, just remember the name, but not, we're not going to get into it much more than that. So CNMR is similar to HNMR in that it counts, this time though, it counts the number of carbons rather than the number of hydrogens. So now remember, hydrogens were about 0 to 10 parts per million. Carbons have peaks that are between 0 and 220 parts per million downfield from tetramethylsilane. You have some common chemical shifts in your textbook on page 410. But again, like before, the shift depends on the electronegativities of nearby atoms. So the more de-shielded a carbon is, the more electronegative atoms it has nearby, the further left the peaks will be. So this is actually the same chart that you have in your book. So you can see that, you know, sp3 hybridized carbons tend to be down here around 20. If they're made two bonds, they're a little bit further left. If they're triple, like tertiary carbons, they're a little further left. If they're bonded to a halogen, if they're bonded to a nitrogen, further left, more and more electronegative. A C single bond O will be in this range. A C triple bond C will be down here around 80. C triple bond N aromatic, and C double bond C tends to be in the 120 range, and then a C double bond O is way further to the left. So here's just some examples. This time there's no splitting the way there is in hydrogen. So this should make sense that the C double bond O is the furthest to the left. This carbon that's between the C double bond O and a Cl is probably this one here, the next furthest left. This carbon here is right next to the O, but only the O. So this purple carbon has 2 electronegative groups, whereas this one just has 1. So it's this one here around 40. And then the furthest one over here to the right is around, looks like about 12. One thing that you need to be able to do is you need to be able to predict how many peaks you would be expecting. So in other words, how many different carbons would you expect? So let's look at this one and see if we can figure that out. And they will have to be non-symmetrical. So here we've got, this is 1, and they're different. Now these 2 look like they're going to be the same. And then these 2 look like they're going to be the same. So I would expect 1, 2, 3, 4 different peaks. These would be twice as many, and then 1, 1, 2, 2. How about this one? Now you might want to notice that this one, the ones that I'm highlighting, they should be the same. So that's 1 peak. Here's a second peak, 2. This is a third one, 4th one, and then a 5th one. And you might say, wait, but is this one the same as this one? Not really, because this has 2 carbons attached and this one only has 1 carbon attached. So you want to look for symmetry. Now, having said that, peak 2 and peak 4 are probably going to be pretty close to each other. They may even overlap a little bit, but they may be distinct peaks. So you would expect 5 distinct peaks. How about this one? We've got 1 here. This is 1. This is going to be a little bit different because it doesn't have the CH3 attached. This one is going to be different. 5. They're technically all different. There's 7 of them. Now, again, having said that, these right in here might be they probably be very, very similar, and they're probably overlap. Like 5 and 6 are going to be pretty close. But technically, there's 7 distinct carbons here. How about this one down here on the left? These 4 are all identical, so that would be 1 kind, and then these 2 are identical, so you should only get 2 peaks in this one. This one is going to have more because of the bromine, so we've got this one will be different, that one will be different, this will be different because it's got 2 of those groups here, and then believe it or not, these are going to be different. And we talked about that before because this carbon is closer to the bromine than this one is. So they're going to be slightly different. So I got my numbers there. All right, we can see that. All right, just look at a couple more examples. Again, we said this one has 2 possibilities. The one that's got the double bond should be further to the left. The 4 that have the single bond are over here. Now there's 4 carbons over here, so this will have an integration of 4, and this one will have an integration of 2. These 1s and 2s are just labels. This carbon that we said, these 2 are identical, and then 2, 3, 4, 5. Of course, the one on the C double bond O should be the furthest over here. That's an equivalent of 1. Again, what I was saying here, 2 and 4 are pretty close to each other. And so 2, because of the extra carbon, is slightly to the left of 4. 5 is the furthest away from everything, so it's over here. And then these 2 over here are, and notice that that's got an integration of 2 because there's 2 carbons. And so this one is going to be a little bit hard to tell, but like we saw, there's 4 different carbons, and you can see 1, 2, 3, 4. I think the more bonds that you have, the further to the left you are. So definitely the CH3 is the furthest over here to the right. This would be carbon number 1. And I would say carbon number 2, now this one's tricky. Carbon number 2 is actually bonded to 3 other carbons, so I'm not sure which one of these 2 here furthest left will be number 2. And you may have to look at the integration to know if it's 1 or 2 carbons. So that's why I'm thinking maybe the one on the left is carbon number 3 and the one on the right is carbon number 2. But 2 should be, the more bonding we have, the further to the left, which is kind of odd because carbon number 4 also is bonded to 2 others, so it's 3. So this is number 4 here, and the integration would tell, but you can see that they're all pretty close to each other. And then one more example was that last one. You could see that, like we said, technically there's 7 different carbons. Each one is very different. And if you look at this, you can see obviously the 2 that are double bonded are the furthest to the left, and the number 1 here, because it's also bonded to an extra carbon, will be a little bit further left than number 2. And then the rest are really close to each other, and so it'd be really hard to tell which one's which. So number 5, actually, this one over here at the end might be number 5. Come on around here to the end. And then 4, 6, 7, and 3 are all going to be really close to each other. So it might be really hard to tell, but you can, at least you can pick out the ones that are most important. So that we're not going to do nearly as much with carbon NMR, but it's helpful to be able to identify the number of different carbons that you have and approximately where you might find them.